Hello everyone, today I want to continue my playlist on classical mechanics and I want to talk a lot more about unit vectors in this video. So in 2D Cartesian coordinates, which is just basically what you're used to, we have an x-axis and a y-axis. But if we really want to talk more about unit vectors, we really need to take this to the third dimension, which I will call z. Now I'm going to show you 3D Cartesian coordinates. We have our y-axis here, our x-axis here. That's our z-axis. So I just tape these three markers together like this because I want you to see the proper depth that's not just on paper. Okay, so really fast, I want to tell you why I set it up with x here, y here, and z pointing up. It's because I'm using what's called a right-handed three-dimensional chord plane. So what this means is that if we take x and we cross it with y, we should get z. So I'm going to take my right hand, I'm going to set it on x with my thumb. You can see there it points up. And here I can pull this part of my hand into the y-axis from x. Always in physics, use a right-handed 3D coordinate plane. You will set yourself up for failure if you don't, in every single problem you do. So, now that we have this defined, it's a right angle between all three of these. I know it's not perfect because it's markers taped together, but you can use your imagination. Always use this. And now I want to use the third dimension to talk about a new definition for the cross product. Okay, I'm going to go ahead and move this out of the way. Okay, so here's our new definition for the cross product. Just a little reminder, A cross B, that's how we write our cross product, two vectors, and we'd say that the magnitude of this equals AB sine of theta, the angle between them. I want to show you a different way to calculate this, assuming that you don't know the magnitude of A and that you don't know the magnitude of B. Okay, so what you can do is, if you know the component's magnitude, you still do have to know something, but if you know the component's magnitude, then we can set this up as three rows of a determinant. Don't be too worried if you don't understand what a determinant is right now. But what we're going to do is we're going to draw a line here. Okay, and I'm going to write our unit vectors, x hat, y hat, and our newest one, z hat. Next, I'm going to write the a and the x, so that's just the x component of A and the y, A and the z, and then I'm just going to do the same thing for B. Alright, now what I can do is I'm going to kind of project this over to the left and the right, so to speak. I'm just going to continue this pattern. Again, don't worry too much if you're unsure about what the determinant is. But if you can remember this setup, it'll give you a really helpful formula for calculating the cross product that's rather lengthy, so that way you don't have to remember that formula. Trust me, this is much easier to memorize. So what we're going to do is we're going to follow a couple different steps. we're going to start with the unit vector. I'm going to start with x. And we move diagonally down and to the right. Okay, so we see a in the y, b in the z, and we stop. So we can say, just write this down. Now, we're going to do the same thing, but we're going to go to the left. So we see a in the z, b in the y. Now subtract the two values and make sure to put it in the x hat direction. Now to this, we are going to add, do the same thing for y hat. I'm going to start to the right, 1, 2. A in the z times b in the x minus a in the x times b in the z. So once again, I'm just following this pattern. And now we're going to add that value to z hat, so a in the x, b in the y. And then you can also just remember that the second term in each set of parentheses is just kind of the opposite of this. So instead of a in the x, it'll be a in the y. And instead of b in the y, it'll be b in the x. Okay, and we can get the same result from doing our rule. Okay, so this formula is also equal to the magnitude of a cross b. Okay, so this can help you if you know the components of a in the x, y, and z directions and b in the x, y, and z directions, but you don't know the magnitude of a and b themselves. Okay, really fast here, just to kind of wrap things up, I want to propose a formula to you, and it's going to be very similar to the Pythagorean theorem. And I mean, it basically is just a three-dimensional Pythagorean theorem. So in 2D, we had a squared plus b squared equals c squared. And we can kind of write the same thing here. This time, we're just going to we're going to do it for some vector a, okay? So, if I take a vector a, the magnitude in the x squared plus the magnitude in the y squared plus the magnitude in the z squared is going to be equal to the magnitude of vector a squared. Okay? And you could take the square root of either side and just write it as though the magnitude of vector a is equal to the square root of a in the x squared plus a in the y squared plus a in the z squared. Okay? That's another very useful formula to know if you are going to be determining the magnitude of a vector in 3 dimensions. Alright, well that is going to do it for this video. Thank you so much for watching. As always, have a good day, have a good night, good afternoon, wherever you are, whatever time you're watching this.